Okay, let me ask you a question. If I asked you right now, where do you live?
My address.
Yeah. What would you say? You'd probably give me, your street, your city, your zip code.
The standard delivery address? Sure. It's functional.
It's functional, it gets your packages delivered, it works for the post office.
It works for the post office, exactly.
But, if you're a regular listener to this deep dive, we don't really do functional here. We don't do small talk.
We do very, very big talk.
We do big talk. So I want to try a little experiment to kick us off. Let's build your full address, your objective cosmic address, the one that tells you exactly where you are in reality.
Okay, I'm with you. So line 1 is easy, planet Earth.
Right. The rock we're all standing on. But let's zoom out immediately. You leave the atmosphere, you pass the moon, which is about a light second away, which is already kind of a mind bender.
Right, already delay.
And you're in the solar system. This is our local neighborhood. You've got the sun, the planets, the Kuiper Belt, all that stuff.
And it's so important to get the scale of this right from the start, because our brains are they're not built for these numbers. So let's try an analogy.
I love a good analogy. Lay it on me.
Okay, if the sun was a grapefruit sitting right here on this table,
Oh, grapefruit. Got it.
then Earth would be a single grain of sand,
Mm-hmm.
about 10 meters, so what, 30 feet away?
Just a speck of dust.
A tiny speck. And Jupiter, the big guy, that would be a cherry pit about a block down the street.
A block away. Wow. Okay, so where does our property line end? What's the edge of the solar system in this model?
In that grapefruit model, you'd be talking miles away.
Yeah.
In reality, the sun's gravity is holding on to comets way out in what's called the Oort cloud. That extends up to about 1.6 light years away.
A light year and a half. So our front yard is 1.6 light years deep.
And that's the edge of the yard, yeah.
Okay, so we step out of the yard. We zoom out again. Where are we now?
Now you're in the city.
Mm-hmm.
You're in the Milky Way galaxy, a swirling, barred spiral galaxy that contains something like 200 billion stars.
200 billion. And this is where the numbers start to get, like you said, just offensive to the human mind. The Milky Way is 100,000 light years across.
It's just a number.
Yeah.
It's meaningless without another analogy.
Well, the source material we're diving into today, the stars, the definitive visual guide, it had a stat that just stopped me cold. It said if you took that entire solar system we just talked about,
The grapefruit, the cherry pit, everything out to the Oort cloud.
everything, and you shrunk it all down to the size of a quarter,
Okay, a single quarter.
the Milky Way galaxy would be the size of North America.
Yeah, that's the one.
It makes you feel so profoundly small. We are a quarter sitting somewhere in, I don't know, Nebraska.
And we're not even in a nice part of Nebraska. We're out in the suburbs of the galaxy.
We're in the spiral arms.
Oh, but we are just getting started. Because that city, the Milky Way, it isn't floating alone in some void. It's part of sort of a metropolitan area. We call it the local group.
The local group. It sounds like a neighborhood watch committee for galaxies.
It's not a bad way to think about it. It's basically a gravitational dance. You've got us, you've got the Andromeda galaxy, which is our bigger, slightly intimidating older sibling that's actually on a collision course with us.
We should probably mention that.
We'll get back to that in a few billion years. And then there's the Triangulum galaxy, and about 50 or so smaller dwarf galaxies all kind of swarming around.
And this whole group is bound together.
Yeah, all gravitationally bound in a space about 10 million light years across.
But we're still not done with the address?
Oh, not even close. The local group is just a suburb. It's a tiny cul-de-sac on the outskirts of an enormous structure called the Virgo supercluster.
Okay, supercluster. Now we're getting into some serious scale.
Now we're talking. The Virgo supercluster is a structure that is 100 million light years across.
And this is where the source material we're looking at today really, it really blew my mind. Because apparently, for a long time, astronomers thought that was basically it. That was the biggest structure.
Right. The superclusters were thought of as these isolated islands in the universe. You had Virgo over here, another supercluster way over there, but the map changed, and it changed very recently.
It's 2014, right?
Yeah, 2014. We realized that even our own Virgo supercluster is just a small appendage, like a little branch on a massive tree of something incomprehensibly bigger.
So introduce us to the tree. What's the monster's name?
It's called Lania. It's a Hawaiian name.
Lania.
And it translates to immeasurable heaven. And honestly, the name fits. We are talking about a structure that is 500 million light years across. It contains 100,000 galaxies.
Wait. Say that again? Not stars.
No. 100,000 galaxies,
Right.
each with hundreds of billions of stars.
That's just not a number a human can process. And what defines Lania, it isn't just that these galaxies are near each other, right? There's something else going on.
This is the truly fascinating part. It's about movement. It's about flow. If you map the velocities of all these galaxies, all 100,000 of them, they aren't moving randomly. They are all flowing.
Flowing how?
Like a cosmic watershed. Imagine raindrops running down a huge, complex valley. They all follow the contours of the land and flow into streams, then rivers, all heading for the same basin.
So all 100,000 galaxies are flowing. Where?
Towards a mysterious, massive gravitational anomaly at the center that we call the Great Attractor.
The Great Attractor. That sounds like the villain in a Marvel movie.
It's so ominous.
Yeah.
And we can't even see it properly. The dust and stars in our own Milky Way block the view.
Yeah.
But we know it's there. We can see its pull.
We can feel it.
We can feel it. Our entire galaxy right now is falling. We're hurtling through space at millions of miles an hour towards this great gravitational drain in the universe.
So let me try to recap my full address then. It's Earth, the solar system, the Milky Way galaxy, the local group, the Virgo supercluster,
Which is just a branch of.
a branch of the Lania supercluster, currently in free fall towards the Great Attractor.
That is your complete cosmic address.
Well, that sets the stage perfectly. Today, we are doing a deep dive into the stars, the definitive visual guide to the cosmos. And as you can probably tell, we are not just looking at pretty pictures, although the book is absolutely full of them.
It's a beautiful guy.
It is. But we're going to try to unpack this whole hierarchy of the universe. We're going to look at the machinery inside the stars themselves, and maybe most importantly, the history of how we, these tiny little humans on a speck of dust, figured any of this out.
It's the ultimate perspective shift, isn't it? I mean, you go out on a clear night away from the city lights, and the sky looks so peaceful.
It's static. It's a picture book.
Exactly. It feels like a beautiful, unchanging wallpaper that was just put there for us to look at, a collection of patterns, constellations.
But the reality is we're starting to see is anything but static.
It's the opposite. It is violent, it is creative, it's cyclical, and it's all governed by a kind of physics that is just. It's almost impossible to comprehend on a human scale. It's a machine, and we happen to be living inside it.
So let's start at the beginning, and I mean the actual beginning. The source material takes us back to the ultimate date stamp, 13.8 billion years ago. The Big Bang.
The moment the clock started ticking.
Right. And I think we hear that phrase, the Big Bang, so often that it sort of loses its punch. It becomes this cartoon image of an explosion.
Well, E. Coyote with a big firecracker.
Exactly. But the timeline the guide lays out is just wild. We start as a tiny point of pure energy, no space, no time. And then what?
And then, in a fraction of a second, and I mean a fraction so small it's meaningless, like a trillionth of a second, a process called inflation happens. The universe expands trillions and trillions of times over.
Okay, I have to pause you right there. Because when people hear expansion, they think of shrapnel flying out from a bomb into an empty room.
That's the biggest misconception, and it's a crucial one to correct. It was not an explosion in space. It was an explosion of space.
There was no room for it to expand into.
None. Space itself was being created. Imagine a dot on a balloon. As you blow up the balloon, the dot gets bigger, but it's the rubber of the balloon itself that's stretching. The grid paper of reality was getting bigger.
And at this point, it's just pure energy, right? No matter...
The seething, incredibly hot soup of pure energy. But almost immediately, within the first second, that energy starts to condense into matter. E equals mc squared in action. And by the time the universe is just 20 minutes old...
The length of a sitcom?
The length of a sitcom, yeah. Protons and neutrons have already formed. We have the nuclei of the first atoms.
20 minutes to get the basic building blocks of everything we see. That's astonishingly fast.
Yeah.
But then it's like we hit a wall. Or maybe a fog is a better word.
The Dark Ages. And that's not a metaphor.
I always just assumed that Dark Ages meant, you know, no stars yet. But the guide explains it's much more literal than that. It's about visibility.
It's completely literal. See, at this point, you have these atomic nuclei, mostly hydrogen and helium, but it's still so incredibly hot that they can't hold on to their electrons. The electrons are just zipping around free.
A plasma?
A dense plasma. And light does not like free electrons.
Why not?
A photon, A particle of light just can't travel. It moves a tiny distance
Yeah.
and whack, it smacks into a free electron and gets scattered in a random direction. It's like trying to walk through an impossibly dense crowd. You can't go in a straight line.
So light was trapped. The entire universe was an opaque, glowing fog.
Exactly. So if you were somehow there in a magical, heat-proof spacesuit,
It didn't instantly vaporize.
right, you wouldn't be able to see your hand in front of your face. You'd just be immersed in this blinding, uniform glow, a wall of white.
And how long did this last?
For 380,000 years.
Ah.
For all that time, the universe was just waiting for things to cool down.
Just a little bit.
Just enough. Finally, around that 380,000 year mark, the temperature dropped to a point where the protons could finally grab onto those wild electrons and hold them in orbit.
We get stable atoms.
We get the first stable atoms. This moment is called recombination. And the instant those electrons were locked up, the fog lifted. Suddenly, the photons could travel in straight lines across the universe.
And that light is still traveling today, isn't it?
It is. That's the cosmic microwave background radiation. It's the oldest light in the universe. It's a baby picture of the cosmos, a snapshot of the exact moment the fog cleared.
But then here's the irony. Once the fog cleared, it got dark. Really, really dark.
Because there were no light sources yet. The universe was transparent, but it was empty. Just these vast, silent clouds of hydrogen and helium gas drifting in absolute blackness.
For how long?
For a very long time, about 550 million years.
500 million years of darkness. That is a staggering amount of time to just gloss over. I mean, we talk about it like it's a short period, but that's 10 times longer than the dinosaurs existed. Yeah. Just nothing.
Just darkness and silence, waiting for the hero of our story to get to work.
And that hero is gravity.
Gravity, the patient sculptor of the universe. Very slowly, over millions of years, it started pulling those clouds of gas together. Little clumps got bigger. The pressure in the center of those clumps started to build. The heat started to rise, denser and denser and denser, until finally...
Ignition.
Ignition. The first stars switched on.
Let there be light, just 500 million years late.
In cosmic time, that's barely a blink. And once those first stars ignited, things really kicked off. Small galaxies began to form, those merged to form larger ones, and that process of merging and growing is what eventually built the enormous structures, like our own Milky Way, that we see today.
The source also gives a little peek into the future timeline, which I found fascinating. We're at 13.8 billion years now, but it says that around the 8 billion year mark, something fundamental shifted. The expansion started to speed up.
Right. That's when dark energy seems to have taken over as the dominant force. We still have no real idea what it is, but it's some kind of intrinsic property of space that's pushing everything apart faster and faster.
And it's also interesting to note just how late we are to the party. Our entire solar system, the sun, the Earth, it didn't form until the universe was already 9 billion years old.
We're the new kids on the block. The universe had a whole long life. It formed galaxies. Stars lived and died for 9 billion years before we even showed up.
Okay, let's talk about scale again, because it's so fundamental to this. When we talk about looking back in time at the Big Bang or at early galaxies, we're really talking about looking across vast distances.
We are. In astronomy, looking out is looking back. The telescope is a time machine.
So let's define our yardstick properly. The light year. I feel like this gets misused in sci-fi all the time, like, I'll be there in 10 light years, which just, it drives me crazy.
It's a classic mistake. A light year is a measure of distance, not time. It's the distance that light, the fastest thing in the universe, travels in 1 year.
And that number is?
It's about 6 trillion miles, or 9.5 trillion kilometers. It's a number so big it's basically useless.
Yeah.
It's just noise to our brains.
Right. So the local examples in the book really help ground it. The moon, for instance.
The moon is about 1.3 light seconds away. So when you look at the moon, you're seeing it as it was 1.3 seconds ago. There's a tangible delay.
And what about, say, Neptune, the farthest planet in our solar system?
Neptune is about 4.5 light hours away.
So if, hypothetically, someone blew up Neptune right now,
we would have no idea for 4.5 hours. We'd be blissfully ignorant watching the aftermath on a 4.5-hour time delay.
And then you go to the next star over, Proxima Centauri, that's 4.2 light years away.
Right. So if they sent us a hello signal today, we wouldn't get it until 4.2 years from now. If we replied hi back, they wouldn't get our response for another 4.2 years.
That's a very, very slow conversation.
It makes long-distance relationships look easy.
Okay, but this brings us to a concept that I know trips people up all the time, and I really want to unpack it carefully. The difference between the observable universe and the Well, the whole universe.
This is such a critical distinction. The universe itself, the whole thing, might be infinite. We don't know for sure, but it's a real possibility. It might just go on forever in every direction.
But we can't see all of it.
We can't.
Mm.
The observable universe is finite. It is simply the region of space from which light has had enough time to reach us since the Big Bang happened 13.8 billion years ago.
It's a bubble of visibility.
It's a sphere of visibility, and Earth is, by definition, at the center of that sphere.
Which sounds incredibly egocentric. You know, we are the center of the universe. Aristotle would be so happy.
It sounds that way, but it's purely a matter of perspective. The best analogy is being on a ship in the middle of the ocean. The horizon forms a perfect circle around you. You are at the center of your horizon, but that obviously doesn't mean you're at the center of the entire ocean.
That's a great way to put it. So our horizon, our sphere, is about 93 billion light years across.
But hang on, I need to challenge you on the math there. I know you know the answer, but for everyone listening,
It's the most common question I get.
if the universe is only 13.8 billion years old, how can the bubble be 93 billion light years wide? Shouldn't it be, 13.8 billion light years in radius?
It's a perfectly logical question. And the answer goes right back to what we said earlier. Space itself is expanding. Think about the most distant galaxy we can see. The light from that galaxy has been traveling for, say, 13.5 billion years to reach our telescopes.
Okay.
But while that light was on its long journey, the space between us and that galaxy was stretching. The universe was expanding the whole time.
It's like trying to run towards someone on a treadmill that's moving backwards and getting longer.
That's a perfect analogy. The light is moving forward, but the treadmill space is carrying the starting point further and further away. So by the time the light finally reaches us, that galaxy is now much, much farther away than it was when the light left. So it's now about 46.5 billion light years away, even though its light only traveled for 13.8 billion years.
Exactly. And since that's true in every direction, you get a sphere that's 93 billion light years in diameter.
Okay, that makes sense. But the source material brings up this thought experiment that I just absolutely loved. It's about planet A.
Yes. This is where things get really existential. Imagine a hypothetical planet, let's call it planet A, that is located way outside our observable sphere. Maybe it's 50 billion light years away from us.
Okay, so I'm on planet A now. I've got my telescope out.
From your vantage point on planet A, you have your own observable universe. You're the center of your own 93 billion light year sphere.
So my bubble and your bubble might overlap.
They would overlap in the middle, yes. We could both see some of the same galaxies that are between us. We could share a patch of reality.
But there's a limit.
There's a hard limit. There are galaxies on the far side of your bubble, relative to me, that I can never, ever see. The light from them will never reach Earth. And likewise, there are galaxies on the far side of my bubble that you on planet A can never see.
We are locked in our own bubbles of reality.
We are causally disconnected. And if the universe truly is infinite, then there are an infinite number of these bubbles, these spheres of observation, stretching on forever. Infinite pockets of reality that can never interact with us, never see us, never know we exist.
That is deeply humbling and honestly a little terrifying. It means there could be entire cosmic empires rising and falling, stars exploding, dramas playing out, and we are physically forbidden from ever even knowing about them.
It's a fundamental limit imposed by the speed of light, the ultimate cosmic wall.
Well, let's bring it back to the people who tried to figure all this out long before we knew about light speeds and expanding space. The history section of this guide is just this incredible story of humanity getting things wrong for a very long time and then slowly, painfully getting them right.
It's really a story about the progression of humility. We always start by putting ourselves at the center of everything. And it begins, really, with Aristotle in the 4th century BCE.
The Earth-centered universe guy.
The geocentric model, yes. But you have to give him some credit. For the time, it was a sophisticated and logical model. He saw the universe as finite, with the Earth stationary at the very center, surrounded by 55 crystalline spheres.
Like a giant set of Russian dolls.
Exactly. And these perfect spheres carried the moon, the sun, the planets, and finally the stars. It was beautiful, it was orderly, it felt right.
It made us feel special. Everything literally revolved around us.
But there were dissenters, even back then. The guide points out Aristarchus of Samos.
Ah, the unsung hero.
He really is the unsung hero of cosmology. In the 3rd century BCE, we're talking over 2,000 years ago, he proposed a sun-centered, a heliocentric universe. He said the Earth orbits the sun, and he even went a step further and said that the stars are just other suns, but they're really, really far away.
He absolutely nailed it. He got it right 2,000 years early. So why didn't anyone listen to him?
Because it completely defied common sense and observation at the time.
Yeah.
I mean, think about it. If the Earth is spinning on its axis and hurtling through space at thousands of miles an hour, why don't we feel a constant massive wind?
Good point.
Why don't things just fly off the table? And most scientifically, why don't the stars shift their positions as we move from one side of our orbit to the other?
The parallax problem.
Exactly. If you hold your finger up and close one eye, then the other, your finger seems to jump against the background. We should see the same thing with the stars over a 6-month period. We don't. Or they couldn't see it then.
And Aristarchus' answer was?
His answer was correct. He said, the stars don't appear to shift because they are unimaginably far away. But no one could accept that the universe was that big. It felt wrong. It was too empty, too vast. So humanity stuck with the cozy, Earth-centered crystal spheres for another 2 millennia.
Until we get to the Renaissance. Copernicus comes along in 1543 with the detailed mathematics to prove the sun is at the center. But the figure I really want to talk about is Giordano Bruno.
Bruno is one of my absolute favorites. He was a true radical, a poet and philosopher as much as a scientist. In 1584, he didn't just put the sun at the center. He looked up at the stars and took Aristarchus' idea to its logical conclusion.
He said they're not just lights on a sphere.
He said, those are other suns, and those other suns have their own planets. And those planets, he argued, have their own living beings on them. He proposed an infinite universe with infinite worlds and therefore no center at all.
He completely shattered the crystal spheres, and, well, he paid the ultimate price for it.
He was burned at the stake by the Inquisition in Rome. His ideas were considered heresy.
For claiming the universe was infinite.
Among other theological arguments, yes. But the idea of an infinite, centerless cosmos was profoundly dangerous to the established order. It made humanity and Earth insignificant.
But then, really interestingly, this idea of an infinite universe created a brand new problem, a logic puzzle. Johannes Kepler brought it up around 1610, and it later became known as Olber's paradox.
Right. This is such a great brain teaser. Kepler actually used this paradox to argue against an infinite universe. His logic was really simple and elegant.
Walk it through it.
He said, okay, let's assume the universe is infinite and it's static and it's filled with an infinite number of stars scattered more or less evenly.
Okay, sounds reasonable.
Well, if that's true, then no matter where you look in the sky, in any direction, your line of sight should eventually end on the surface of a star.
Right, like standing in the middle of a very, very dense forest. Everywhere you look, your view is blocked by a tree trunk.
Exactly. So if the universe is an infinite forest of stars, the entire night sky should be ablaze with light. It shouldn't be dark. It should be as bright as the surface of the sun, everywhere, day and night.
But the sky is dark.
The night sky is profoundly dark. So Kepler concluded, therefore the universe is not infinite. It has to have an edge, a wall.
And we had to wait for the modern era to finally solve that one. How do we resolve Olber's paradox? Why isn't the sky glowing white?
It took until the 20th century and 2 huge discoveries. The first came from Edwin Hubble in the 1920s. He proved that the universe is expanding.
The redshift.
The redshift, exactly. He saw that distant galaxies are all moving away from us. And because they're moving away, the light from them gets stretched to longer, redder wavelengths. The light from the most distant stars is stretched so much that it shifts right out of the visible spectrum and into the infrared.
So the light is still hitting us, but our eyes just can't see it.
That's the first part of the solution. The sky is dark because much of its light is invisible to us. And the second part of the solution is...
The universe had a beginning.
Correct. It hasn't been here forever. Light travels at a finite speed. So there are stars that are so far away that their light simply hasn't had enough time in the 13.8 billion year history of the universe to reach us yet.
So we're not seeing an infinite wall of trees because we can only see the trees that are close enough for their light to have reached us. The forest has a temporal horizon.
That's the perfect way to put it. It's just amazing how that simple, naked eye observation, the sky is dark, can lead you to the profound conclusion that the universe must be expanding and have had a beginning.
And then came the smoking gun. The final piece of evidence for that beginning, Penzias and Wilson, 1965.
The guys with the antenna.
The guys with the antenna and the pigeons.
Yeah, 2 radio astronomers in New Jersey. They were trying to calibrate this very sensitive horn antenna, and they kept picking up this persistent, faint hiss. a background noise.
And it drove them crazy.
Drove them crazy. They pointed the antenna everywhere. They thought it was interference from New York City. They famously found pigeons nesting in the antenna and thought it might be, and I quote, white dielectric material.
Pigeon droppings.
Pigeon droppings. So they cleaned it all out. They literally scrubbed the pigeon poop off the dish.
And the hiss was still there.
The hiss remained. It was coming from every single direction in the sky, day and night, with the same intensity.
And eventually they realized they weren't hearing pigeons, they were hearing the echo of the Big Bang.
They had stumbled upon the cosmic microwave background, that afterglow from the moment of recombination we talked about, the faint heat left over from the creation of the universe, now cooled down to just a few degrees above absolute zero.
And they won the Nobel Prize for it. It's the best story. The guys who cleaned up pigeon poop and found the echo of creation.
It's fantastic.
Okay, so we know where we are in this vast structure, and we have a pretty good idea of how it all began. Now let's zoom back in and look at who our actual neighbors are. The demographics of the sky.
The census of the Milky Way.
Right. So we've got something like 200 billion stars in our galaxy alone. But when we go outside and look up, we're only seeing a tiny fraction of that, right?
A minuscule fraction. On the best, darkest night, from a perfect location, the human eye can see maybe 9,000 to 10,000 stars, and most of what you're seeing are the exceptions, the freaks, the giants and supergiants that are unusually bright.
Not the average citizen.
Not at all. The vast majority of stars are too faint to see without a telescope.
So what actually counts as a star? Where do we officially draw the line?
The definition is actually very strict. A star is a ball of gas that is massive enough to ignite and sustain nuclear fusion in its core. Specifically, it has to be fusing hydrogen into helium.
If it's not doing that, it's not a star.
Not a true star, no. If an object is big but not quite massive enough to kickstart hydrogen fusion, say somewhere between 13 and 80 times the mass of Jupiter, we call it a brown dwarf.
A failed star.
A failed star. They glow dimly from their own internal heat, but they're not self-powered by fusion in the same way.
And if it's smaller than that?
Then it's a planet. It's just reflecting light from its parent star. It's not generating its own.
So let's talk about how we classify the real stars. The source breaks it down with this letter system. O, B, A, F, G, K, M.
The spectral classes. And generations of astronomy students have memorized that sequence with the mnemonic, oh, be a fine girl or guy kiss me.
It's definitely catchy. And this sequence is all about temperature and color. But this is one of those things that's completely counterintuitive for anyone who's ever looked at a bathroom faucet.
It really is. In our daily lives, we're conditioned to think red is hot and blue is cold. But in physics and in fire, it's the complete opposite.
You just have to think of a blowtorch flame.
That's the perfect image.
Right.
The hottest part of the flame is the brilliant blue part. So the O-class stars are the hottest. They're blue-white, and they burn at over 54,000 degrees Fahrenheit, or 30,000 Celsius. They were just screaming hot.
And the red ones, the M-class stars.
The M-class stars are the coolest. They're down around 5,300 degrees Fahrenheit.
I mean, still hot enough to completely ruin your day.
Oh, absolutely.
Yeah.
But on the stellar scale, they're the chilly ones.
And our sun. Where do we fit in?
Our sun is a G-class star, a pleasant yellow-white star, right in the middle of the sequence. A solid, pretty mediocre surface temperature of about 9,500 degrees Fahrenheit.
I just love that our sun is basically a medium t-shirt size in the universe. It's not too hot, not too cold. It's totally average.
It is wonderfully, beautifully average. And this brings us to what might be the single most important chart in all of astronomy, the Hertzsprung-Russell diagram, the HR diagram.
Okay, this sounds very technical, but the way the visual guide lays it out, it just looks like a map of the stellar population.
That's exactly what it is. It's the Rosetta Stone for understanding stars. All you do is you plot a star's true brightness, its luminosity on the vertical axis, and its temperature or spectral class on the horizontal axis.
And when you plot thousands of stars, a pattern emerges.
A very clear pattern. You find that about 90% of all stars fall on a smooth diagonal line that runs from the hot, bright blue stars in the upper left down to the cool, dim red stars in the lower right.
The main sequence.
The main sequence. This is where stars spend the vast majority of their lives. Our sun is right in the middle of the main sequence. It's stable, it's, paying its taxes, going to work every day, steadily fusing hydrogen into helium.
But you also have these outliers, these other groups on the chart.
You do. Up in the top right quarter, you have the giants and supergiants.
So those are cool because they're on the right side of the chart, but they're very bright.
Exactly. They are cool, so they are reddish, but they are incredibly luminous because they are enormous. Their surface area is huge. These are stars that are in their death throes. They've swollen up. Betelgeuse is a classic example.
And then you have that other cluster down in the bottom left.
The white dwarfs. The stellar corpses. They're very hot, so they're on the left side, but they're incredibly dim because they are tiny, about the size of the Earth.
So let's pop the hood on one of these main sequence stars. Let's use our sun as the model. How does this machine actually work? You said fusion is pushing out, but what's fighting it?
A star is a constant, perfectly balanced war. There are two titanic forces fighting for control. The first is gravity.
Right.
Gravity's relentless. It's pulling every single particle of the star inward, trying to crush the entire thing down into a single point. It wants to collapse the building.
So gravity is the great crusher. What's pushing back?
The nuclear fusion in the core. The immense heat and light generated by that fusion creates an outward pressure, a radiation pressure.
So it's an explosion pushing out against a collapse pulling in.
It's a perfect stalemate. We call it hydrostatic equilibrium. You can think of it like a bomb that is detonating continuously, but the sheer weight of the star's own outer layers is so heavy that it contains the explosion. As long as the star has fuel to burn in its core, that outward pressure perfectly balances the inward pull of gravity.
And the star is stable.
Perfectly stable for billions of years.
But the journey of that energy from the core where it's created to the surface where we see it is it's incredible. The source material says it can take 100,000 years for a single photon to get out.
It's one of my favorite facts in all of science. That first part of the star's interior, the radiative zone, is unbelievably dense. It's about 150 times denser than water on Earth. So a photon, a little packet of light energy, can't just fly in a straight line.
It's too crowded.
It's a cosmic mosh pit. The photon travels a tiny fraction of a centimeter, and bam, it smacks into a proton. It gets absorbed and re-emitted in a random direction. Then it hits an electron, bounces again, we call it the random walk.
A drunken stumble to the surface.
It is a 100,000-year-long drunken scumble.
That is just wild. It means the actual sunlight hitting my face right now, the warmth on my skin, that energy was created in the core of the sun before modern humans even existed.
That is absolutely correct. That specific photon of light was forged in the Stone Age, spent the next 100,000 years fighting its way out of the sun, and then zipped across the 93 million miles of space in just 8 minutes to hit your face.
That really changes how you think about getting a sunburn.
It does. Now, once it gets past that incredibly dense radiative zone, things get a bit easier. It hits the convective zone.
And this is more like...
This is more like a pot of boiling water or oatmeal. Hot blobs of gas physically rise to the surface, release their heat into space, cool down, and then sink back down to get heated again.
And the surface that we actually see, the part that looks like a surface, is the photosphere.
That's the visible surface. But the sun has an atmosphere above that too. There's the chromosphere, which is this sort of irregular spiky layer, and then the corona, that beautiful wispy outer crown you see during a total solar eclipse.
And the corona has that weird mystery about it, right? The temperature.
It's one of the biggest unsolved mysteries in solar physics. The surface of the sun, the photosphere, is about 10,000 degrees Fahrenheit. But the corona, which is much farther out, is millions of degrees.
It gets hotter as you move away from the fire.
Exactly. It's like walking away from a campfire and suddenly getting hotter.
Yeah.
We have theories about magnetic fields and plasma waves, but we're still trying to figure that one out for sure.
I want to touch on brightness, because this is another one of those things that really tricks our eyes when we look at the night sky. The difference between apparent magnitude and absolute magnitude.
This is so crucial to understanding what you're actually looking at up there. Apparent magnitude is the simple one. It's just, how bright does that star look from my backyard?
And the scale is backwards, an old Greek system, right? The lower the number, the brighter the object is.
Exactly. So the sun is a ridiculous negative 26.7. The full moon is about negative 12. The brightest star, Sirius, is negative 1.5. And the faintest stars you can see with your naked eye are about +6. This is completely deceptive.
Because distance is the great variable. A dim light bulb up close can look brighter than a giant searchlight far away.
Precisely. The example used in the text is a great one. Alpha Centauri versus a star called Hadar. When you look up at the Southern Cross constellation, they look like they're right next to each other. They look about the same brightness.
Like they're twins in the sky.
But Alpha Centauri is our next-door neighbor. It's only 4.4 light-years away. Hadar is roughly 390 light-years away.
So wait, for Hadar to look just as bright as Alpha Centauri, even though it's almost 90 times farther away?
It must be an absolute monster. It has to be intrinsically, incredibly powerful.
Yeah.
If you could somehow take both stars and line them up side by side at a standard distance, Hadar would outshine Alpha Centauri thousands of times over. And that intrinsic brightness is its absolute magnitude.
So when we look at the night sky, we are not seeing a fair lineup at all. We're seeing a jumbled mix of dim stars that happen to be very close to us and absolute cosmic powerhouses that are so far away they just look like faint pinpricks.
Exactly right. It's a total optical illusion of depth.
Let's get into the life stories of these stars.
Yeah.
Because they aren't immortal, they are born, they live, and they die. And the source makes it incredibly clear. Mass is destiny.
Mass is everything. How much gas and dust you start with in the beginning determines absolutely everything about how you will live and how you will die.
So let's start with the birth. Where do stars come from?
They're all born in nebulae. These vast, cold, beautiful clouds of gas and dust. Gravity does its patient work, pulling the gas into denser and denser clumps. These clumps start to shrink and heat up, and we call them protostars.
And stars are often born in big groups, right? Not alone.
Yeah, they're born in litters. We call them star clusters. You have open clusters like the Pleiades, the Seven Sisters, which are young and will eventually drift apart. Or you can have enormous, ancient globular clusters like M15, which are dense balls of hundreds of thousands of old stars.
Okay, so a star is born. Let's look at the three main life paths based on mass. Scenario A, the little guys, the low mass stars, the red dwarfs.
These are the tortoises of the universe. They're by far the most common type of star. About 75% of all the stars in the Milky Way are red dwarfs. They're small, they're cool, and they're incredibly efficient with their fuel.
They're the little hybrid cars of the cosmos. They sip their fuel.
They sip it so slowly that their potential lifespan is trillions of years.
Trillions! Wait, but the universe is only 13.8 billion years old.
Exactly. And that leads to an amazing fact. Every single red dwarf that has ever been born in the history of the universe is still alive today. Not a single one has had time to die of old age yet.
That's incredible. They're all still just in their infancy. But what will happen to them eventually in the far, far future?
Their death will be very quiet. They don't have enough mass to do anything dramatic. They will just slowly burn through all their hydrogen, maybe get a little hotter for a while and turn into a hypothetical blue dwarf, and then they'll shrink down into a white dwarf and just fade away into a cold, dead cinder called a black dwarf.
Okay, scenario B, the medium mass stars, the middle class, stars like our sun.
Right. Our sun has a total lifespan on the main sequence of about 10 billion years. We're about 4.6 billion years in, so we are comfortably middle-aged.
So what happens at the retirement party in another 5 billion years?
It's not a gentle retirement, I'm afraid. When the sun runs out of hydrogen fuel in its core, the delicate balance breaks. Gravity starts winning, and it crushes the core.
The building starts to collapse.
But that collapse raises the temperature and pressure so much that it ignites a shell of hydrogen fusion around the dead core. This extra burst of energy causes the sun's outer layers to expand massively.
It becomes a red giant.
A huge, bloated red giant. It will swell up enough to completely swallow Mercury, Venus, and very possibly Earth itself.
Not a great day for real estate values on Earth.
No. Even if the Earth isn't physically swallowed, the intense heat will boil our oceans away and strip our atmosphere. It's game over. But eventually, those bloated outer layers will drift away from the core, forming a beautiful, glowing shell of gas we call a planetary nebula.
And the core itself, what's left behind?
The hot, dead core is left behind, exposed to space. It becomes a white dwarf. It's an object about the size of the Earth, but it still has about half the mass of the sun packed inside it. It's incredibly dense. A single teaspoon of it would weigh several tons.
And it just sits there and cools off.
It just sits there and radiates its leftover heat into space, slowly cooling for billions and billions of years. That is the ultimate fate of our sun. A beautiful nebula, and then a slowly cooling diamond in the sky.
Okay, now for the main event. The action movie stars. Scenario C, the high mass stars.
These are the rock stars of the cosmos. The live fast, die young, leave a good-looking corpse crowd, or at least a very dramatic one. If you're born with 8, 10, 20 times the mass of the sun, you don't live for billions of years. You live for a few million.
Because their gravity is so immense, they have to burn their fuel at an insane rate.
They are absolute gas guzzlers. To generate enough outward pressure to fight off their own crushing gravity, they have to burn through their fuel at a ferocious pace. They become luminous, enormous red supergiants, like Betelgeuse and Orion.
And when they run out of hydrogen in their core, they don't just stop like the sun does.
No, they're so massive they can keep going. The core crushes down, gets hotter, and they start fusing helium into carbon. When the helium runs out, they crush again and start fusing carbon into neon, then neon into oxygen, into silicon. They forge heavier and heavier elements in concentric shells, like a cosmic onion.
Until they hit the ultimate wall, Iron.
Iron is the kiss of death for a massive star.
But why iron? What's so special about it?
Because up until iron, every fusion reaction releases energy. Fusing hydrogen to helium gives you energy. Fusing helium to carbon gives you energy. That energy is what holds the star up against gravity. But fusing iron, it actually consumes energy. It takes more energy to fuse iron than you get back.
So the engine doesn't just stall, it goes into reverse.
Instantly. The moment a critical mass of iron builds up in the core, the furnace switches off, the outward pressure vanishes in an instant, and gravity wins, decisively and catastrophically.
And the core collapses.
The core collapses, going from the size of the Earth to the size of a city in less than a second.
That speed is just terrifying.
The outer layers of the star, which were just sitting there a moment ago, suddenly find they have nothing supporting them. They plunge inward at up to a quarter of the speed of light, slam into that newly formed ultra-dense core, and rebound in the most violent explosion in the universe.
Boom! A supernova.
Supernova. For a few weeks, that single exploding star can outshine its entire home galaxy of 200 billion stars.
And what's left behind in the wreckage? What's the corpse?
Two main possibilities. If the original star was pretty big, say between 8 and 20 times the sun's mass, the core collapse is halted by something called neutron degeneracy pressure. You're left with a neutron star.
And this is where the density gets truly insane.
The core is crushed so tightly that protons and electrons are literally forced to merge together to become neutrons. You have an object the size of Manhattan that has more mass than our sun. It is effectively one giant atomic nucleus. The source says a tennis ball-sized chunk of it would weigh as much as 40 times the entire human population.
That's just no. My brain rejects that. But what if the star was even bigger?
If the original star was more than about 20 times the mass of the sun, then its core is so massive that nothing can stop the collapse, not even neutrons. The core collapses all the way down to a single point of infinite density, a singularity.
A black hole.
A place where gravity is so strong that the fabric of space-time itself is torn. A region from which nothing, not even light, can escape.
This leads us perfectly into the final and I think most poetic concept in the whole guide, this idea of cosmic recycling. Because when that star goes supernova, all that stuff it created, the carbon, the oxygen, the iron, where does it all go?
It gets blasted out into the galaxy at incredible speeds. It enriches the great clouds of gas and dust between the stars, what we call the interstellar medium.
And this answers the ultimate question, doesn't it? Because the Big Bang only made hydrogen and helium and a tiny bit of lithium.
That's right. If the universe only contained the primordial elements from the Big Bang, complex structures like planets and people would be impossible. You can't build a human out of just hydrogen gas.
So the oxygen in the air that I'm breathing right this second.
It was forged in the core of a massive star that lived and died long before our sun was even born.
The iron in my blood that's carrying that oxygen.
Forged in the final frantic moments of a supergent star just before it went supernova.
The calcium in my bones. The carbon that forms the basis of my cells.
All of it is star ash.
So it's not a metaphor. We are literally physically made of star stuff.
We are recycled nuclear waste, to be a little less poetic about it. We are the processed garbage of generations of dead stars.
That is the most profound way to call me trash I have ever heard.
But it connects us to the cosmos in the most direct, physical way imaginable. We are not just observers in the universe. We are made of the universe. The atoms that make up your left hand might have come from a completely different supernova than the atoms that make up your right hand.
And astronomers can actually measure this in other stars, right? This concept of metallicity.
We can. When we look at a star's light, we can see the chemical signatures of these heavier elements, which we call metals. The very oldest stars in the universe are almost pure hydrogen and helium. Younger stars, like our sun, are much richer in these heavy metals because they formed from clouds that had already been seeded or polluted by thousands of previous supernova explosions.
So we are the beneficiaries of millennia of cosmic pollution.
We are. The death of one generation of stars is what provides the raw material for the next generation of stars and planets and life.
So let's try to wrap all of this up. We've gone from the very beginning of time to the violent deaths of stars. We've zoomed out to the Great Attractor. What's the big takeaway here? Because it's very easy to just feel impossibly small and insignificant after a conversation like this.
And that's part of it. I think understanding our true place in the cosmic hierarchy is profoundly humbling. Realizing we are on a tiny rock orbiting an average yellow star, in a quiet spiral arm of one galaxy among hundreds of billions, all falling towards something we can't even see. That's a healthy dose of perspective.
But there's another side to it, isn't there?
There is, because you have to step back and think, look at what we've done. We are these fragile, short-lived biological machines on this one little rock, and using nothing but our curiosity, mathematics, and reason, we have managed to map the structure of Lania. We have looked back to the first second of time. We have figured out the inner workings of stars we can never visit.
From the cozy crystal spheres of Aristotle to the warped space-time of Einstein, it's a heck of a journey for a species that's only been doing recognizable science for a few hundred years.
It's an astonishing achievement, and we are still just scratching the surface.
I want to leave everyone with that thought experiment we talked about earlier. That idea of planet A, the idea that because of the finite speed of light and the expansion of the universe, there are these bubbles of reality that we can never, ever see or interact with.
The horizon, yes.
It just makes you wonder, what is happening right now in those other bubbles? There could be entire civilizations rising and falling. There could be forms of life or physics we can't imagine. Entire cosmic dramas playing out.
And to us, they might as well not exist. And we, to them, don't exist either. We are forever separated by the expanding fabric of space-time.
We're alone in our own little bubble, but we're part of something that is likely infinite.
It's a chilling and a beautiful thought to end on.
Thank you for taking this deep dive into the architecture of the cosmos with us. Go outside tonight if you can, look up, and just remember, you're looking at a history book written in light.
And you're looking at the stuff you're made of. You're looking at home.
We'll see you on the next deep dive.